Firstly, I would like to thank the organisers for the opportunity to speak here. My talk here today is closely related to the talk given by Eric, where I will be focusing on the more technical aspects of the proof. To give a brief introduction, in this work, we show that Bell-Cochen-Specker inequality violations in phenomena satisfying the no disturbance condition, a generalization of no signaling, cannot in general be explained by a faithful classical causal model. In a previous result, this was shown by Eric Cavalcanti for the case of two parties or two measurements per context. Here we generalize this result to an arbitrary number of parties or measurements per context. We also identify an implicit assumption made by the previous proof, whereby certain operational symmetries of the phenomenon are reflected by the model. To begin, I'll briefly review Judea-Pearl's framework for classical causal models. The basic idea is that causal structure is captured by a directed acyclic graph. Random variables are represented by nodes. Causal links are represented by directed arrows or edges. Now, the set of direct causes of a variable are called parents, and the set of effects of a variable are called descendants, while non-effects are called non-descendants. The causal Markov condition is the assumption that a variable x is conditionally independent of its non-descendants, or its non-effects, given its parents, or its direct causes. And so for a graph with variables x1 to xn, the causal Markov condition implies that any probability distribution compatible with the graph factorizes in this way here. And so graphs encode conditional independence relations between variables of the graph. Deseparation is a systematic approach to obtain these conditional independence relations from a graph. Formally, we can say that two sets, x and y, are deseparated given a third set, z, if and only if z blocks all paths in the graph between x and y. And if this is true, then we write the deseparation condition in this form with a subscript d. And so to check whether a deseparation condition holds for a set of variables, we need to check all paths connecting those variables in the graph. And so if a path is a chain or a fork of this form here, then a path is blocked by z if the middle node b is in z. If a path is an inverted fork or a collider, which we call a collider, then the path is blocked if the middle node b is not in z and no descendant of b is in z. And so here are some simple graphs to illustrate deseparation. In the box on the left, x and y are deseparated by z, so they satisfy the condition that all paths between x and y are blocked by z. Whereas the box on the right shows two examples that do not satisfy the deseparation condition, and that's because here z appears as the middle node of a collider, and here z appears as the descendant of the middle node of a collider. The deseparation procedure provides a sound and complete method of obtaining conditional independence relations from a graph. It's sound as if a graph satisfies a deseparation condition, then any probability distribution, P, compatible with the graph, also satisfies the corresponding conditional independence. And it's complete as if all probability distributions compatible with a graph satisfy a particular conditional independence relation, then all graphs will satisfy the associated deseparation condition. The semi-graphoid axioms is a set of rules that can be used to derive additional conditional independence relations. And so here the bold notation just means that the elements in these conditions can be sets of random variables, not just as they don't have to be just a single random variable. Okay, and so now I'll show how Bell and Cochen-Specker scenarios can be represented in this causal framework. And so we define a set of measurements and outcomes in this way. The same set of outcomes can be used for all measurements without loss of generality. A compatibility structure, capital C, is defined to contain all subsets of jointly measurable measurements. The subsets of the compatibility structure form the measurement contexts. A special class of contextuality scenarios are the n-partite Bell scenarios, where the set of measurements can be decomposed into n disjoint subsets, such that the context contains exactly one element from each subset. Quotient-Specker contextuality scenarios we then define as any contextuality scenario that cannot be partitioned in this way. Arbitrary contextuality scenarios, Bell or Quotient-Specker, are simply referred to as Bell KS scenarios. For a given measurement scenario, a set of n compatible measurements are chosen to be performed via the set of random variables x. Likewise, outcomes are recorded by the set of random variables a. Measurement outcome pairs are represented as ordered pairs. And now, for convenience, we introduce a shortcut notation to refer to arbitrary subsets of outcomes and settings. Gamma is defined to be an arbitrary subset of the index labels. And so A gamma and X gamma are arbitrary subsets of A and X. And we also define the complements of A gamma and X gamma by using the set exclusion symbol. And so these are referred to by A exclude gamma and X exclude gamma. And so this brings us to the formal definition of a classical causal model for phenomenon for Bell KS scenarios. A phenomenon is a probability distribution over the observable variables, which can be understood operationally. We use the curly P, this one here, to refer to phenomenon distribution, and a regular P to refer to the model distribution. And so a classical causal model, gamma, for a phenomenon consists of a possibly empty set of latent variables xi, a directed acyclic graph G with nodes AX xi, and a probability distribution compatible with G such that the distribution for the phenomenon is obtained by marginalizing over the latent variables. A phenomenon satisfies no disturbance if and only if it satisfies the following two conditions. The probability for a subset A gamma should only depend on the corresponding set of measurement settings X gamma. And secondly, the measurement statistics for the same measurement should not depend on the label assigned. Now, for Bell scenarios, this second condition is trivially satisfied due to the partitioning of measurements. In a KS scenario, however, the same measurement may be assigned to different labels. And so in Bell scenarios, the no disturbance condition simply reduces to no signaling. And so here's an example with 3 measurements to illustrate the kinds of constraints on a no disturbance phenomenon. The most trivial index subset gamma is just going to be A1, A2, or A3. And so we get 3 constraints of this form. And then there are also going to be constraints for pairs of outcomes, so A1, A2 here, and likewise for there'll be another one for A1, A3 and A2, A3. Now, it's important to note that no disturbance and no signaling are properties of phenomena, meaning that they can be defined operationally. The next definitions that I'm going to go through instead deal with properties of causal models for phenomena, which is to say that they can be considered ontological properties. The assumptions of Bell locality and KS non-contextuality, while conceptually very different, can be both translated mathematically to the language of causal models through the condition of factorizability. A causal model for a phenomenon is factorizable if and only if the model factorizes in this form, where each conditional probability only contains one measurement outcome pair, as well as potentially latent variables. For Quotient-Specker scenarios, The model must also satisfy this second condition. This requirement means that a measurement M has the same marginal statistics in the model, independent of which random variable it is associated with. And so a causal model for a Bell scenario is Bell local if and only if it is factorizable. And a causal model for a contextuality scenario satisfies KS non-contextuality if and only if it satisfies measurement non-contextuality, outcome determinism, and freedom of choice. And so by the Feiner-Abramsky-Bradenberger theorem, the assumption of KS non-contextuality is equivalent to the existence of a factorizable model. The final ingredient that we need is the definition of faithfulness of a causal model. And so a causal model gamma is faithful relative to a phenomenon P if and only if 1. Every conditional independence in P corresponds to a deseparation condition in the graph for the model. And secondly, operational symmetries of the phenomenon are reflected by the model, rather than holding only for special values of the model parameters. The second condition here is an extension on Judea-Pearl's original definition of faithfulness. The only implication of condition 2 that we actually need is that if a phenomenon has the symmetry that the outcome of a measurement does not depend on the label, then a faithful model should satisfy that same symmetry. Okay, so the main result of this work is theorem 1, which says that every phenomenon satisfying no disturbance in an arbitrary contextuality scenario that has a faithful causal model is factorizable. And so from this theorem, two important corollaries follow. First of all, no fine-tuning and no disturbance imply Cauchy-Becker non-contextuality in arbitrary scenarios. And secondly, every classical causal model that reproduces the violation of a Bell-KS inequality for a no disturbance phenomenon in an arbitrary Bell-KS scenario requires fine-tuning. To give you an idea of the direction of the proof, here's a brief sketch. So the first step is to write the most general set of graphs for a causal model of a no disturbance phenomenon. No fine-tuning requires that all graphs obey the deseparation conditions associated with no disturbance. From this, additional constraints beyond those implied by no disturbance alone are found, which then imply additional constraints on the model. These extra constraints are then used to show that the model is factorizable. Due to the sheer number of possible graphs that we need to consider, it's helpful to define a graphical shortcut notation. And so a double-sided arrow here represents the possibility of either a cause from x to y or y to x. An arrow with a triangle from x to y represents a direct cause from x to y with or without a common cause. An arrow with a circle from x to y represents these two possible graphs here, as well as the possibility of a common cause with no direct cause. And then a causal connection with two circles on either end just represents any possible causal connection between x and y. And so the proof proceeds by deriving a set of deseparation conditions that must be obeyed by any causal model satisfying no disturbance and no fine-tuning. The class of graphs we need to consider are those which include latent variables as common causes for observable variables, or direct causes between them. Latent variables that act as a chain or inverted fork between observable variables do not need to be considered, as they have no effect on the allowed probability distribution over the observable variables. From no disturbance and no fine-tuning, we can rule out causal links or common causes between an outcome AI and any setting xj where I is not equal to j. And so this excludes the possibility of a common cause between any two outcomes and a setting, meaning that we can split the set of latent variables into the set lambda, which is common to all outcomes, and omega, which can be common to all settings. And so this leaves us with the class of graphs shown here. This step is just a change in representation. Since we are trying to be as general as possible, there is the possibility of no causal connection at all between a particular member of A and its corresponding setting. And so without loss of generality, we can group all members of A and X into one of two subsets. Subset B contains all members of A with no causal connection to X, while subset C contains all remaining members of A with at least some kind of causal connection, which we now represent using this solid line. Bold nodes now represent sets of nodes, and the dashed notation for a node represents the possibility of an empty set. Now, there is still implicitly a set of latent variables omega acting between y and z here. It's just omitted from the graph here as it does not play a significant role in the next part of the proof. Okay, so from no disturbance and no fine tuning, we can write this deseparation condition here for B, Z, and Y. And now any path between B and Z must pass through at least one element of C. And now since C is not in Y, C must act as a collider. And so direct links from C to B would violate this deseparation condition here. So this allows us to rule out a direct connection from any member of C to a member of B. Now from the set of graphs, we can see that Y cannot act as a middle node between B and Z. We can then write that B and Z are deseparated given the empty set, or any set that does not act as a middle node of a collider in any path between B and Z. Now, since lambda cannot act as a collider in any path, we can say that B and Z are deseparated given lambda. Again, from no disturbance and no fine tuning, we can write this deseparation condition here, which by the symmetry axiom we can rewrite in this form. We can then apply lemma 1 because we can now consider this graph to be a chained graph. And so from lemma 1, we can derive this deseparation condition here. We can then apply the weak union axiom, symmetry, and rewrite BC as A. And by doing all that, we can arrive at this deseparation condition here. Okay, so next we consider the types of causal connections that can exist between members of C. And so to do this, we consider two elements, Ci and Cj in C. From no disturbance and no fine tuning, as well as applying decomposition, we can write that Cj is deseparated by Zi given Zj. And now for a path along Zi, Ci, and Cj, for a path of this form to be blocked by Zi, Ci must act as a collider. And so we can eliminate a direct link from Ci to Cj. And now by symmetry, we can also make the same argument to show that there cannot be a direct path from Cj to Ci. And so direct links between members of C are therefore eliminated. And so this is represented by the class of graphs shown here, where C has explicitly been broken up into a single element Ci and all the other members of C. Okay, so we now look at what deseparation conditions can be derived between members of C. From this graph, we can divide all paths into one of two types. Paths that go through Zi, which is the bottom part of this graph here, and paths that go through B lambda, the top part. So first, looking at paths between Ci and the rest of C through Zi, we can write this deseparation condition here. Note that this is just a condition that Ci is deseparated from all settings that are not Zi, given Zi. And so any path through Zi where Zi is a collider violates this condition. And so any path through Zi must be a chain or a fork with Zi as the middle node. And so Zi then must block all paths as a chain or a fork. Since all paths through Zi must go through Zi first, we can say that Zi blocks all paths between Ci and C exclude I that go through Zi, i.e. paths of this form through any node here. Now considering the rest of the paths through B and lambda, we can see that B and lambda can only act as the middle node of a chain or a fork. And so B lambda blocks all paths through B lambda. Since paths through Zi are blocked at the node Zi, we can write this deseparation condition here, where Z, B, and lambda together block all paths, whether you go through Zi or B lambda. And so this gives us this deseparation condition here. Similarly, just from no disturbance and no fine tuning, we can write this deseparation condition here. And then for the same argument as before, lambda cannot act as a collider. So we can also write this deseparation condition here, where we can add lambda, where lambda is also conditioned on. The final deseparation condition that we need to derive is freedom of choice. That is, lambda is independent of x. To do this, we break up the classes of graphs based on the types of causal connections between Ci and Zi. And so class A contains a direct cause from Ci to Zi with or without a common cause. And class B just excludes a direct cause from Ci to Zi. And so together, A and B contain all the graphs allowed up to this point so far. Taking the class of graphs A, no disturbance plus no fine tuning, imply these two deseparation conditions here, which rule out all connections between Ci, B, and any other member of C. And so paths through B or lambda from C exclude I to Zi need B to be a collider. Since B or lambda cannot be a collider, there can't be any connection between B and Ci, and no common cause between Ci and C exclude I. And so by symmetry, this holds for any path through any member of C that has this type of causal connection to Z. Now considering the class of graphs B, second type, with this type of causal connection here between Ci and Zi, we see that Ci must always be a middle node of a collider for paths of the form lambda Ci Zi. Paths of this type are blocked by the empty set. Since every path from lambda to Z must include a subpath of this form, we can write that lambda and x are deseparated given the empty set. The deseparation conditions derived imply the corresponding conditional independence relations for any compatible distribution for the model. And so from the definition of conditional probability, the joint distribution for Ax, omega, and lambda can be written in this form, where marginalizing over lambda and omega produces the distribution over the observable variables. Then summing over omega using Ci1 and writing x as yz gives us this equation here. We can then write A as BC, apply the chain rule for conditional probability, and use Ci's 2 and 3 to arrive at this form of the equation here. Since B is only dependent on lambda in the graph, without loss of generality, we can let lambda determine B. Any phenomenon compatible with a model of this form will then also be compatible with a model where lambda determines B. B can then be considered fully determined given lambda. And so expanding out the conditional probability for C, we can then apply Ci's 4 and 5 to obtain this form of the conditional probability of C. Similarly, we can do the same thing for B. And then we can put this together to obtain a factorizable model for any phenomenon satisfying no disturbance and no fine-tuning. For Bell scenarios, where each measurement is performed by a single party, this completes the proof. Now, for Cauchy-Specker scenarios, a further step is needed. From the definition of no disturbance, a no disturbance phenomenon satisfies the operational symmetry of an exchange of labels. A faithful model must satisfy the same symmetry, and so this imposes the corresponding label symmetry constraint for any faithful model. And so this completes the proof for Cauchy-Specker scenarios and highlights a key distinction between Bell and Cauchy-Specker scenarios. To summarize, we have shown that Cauchy-Specker contextuality and Bell nonlocality in fully general scenarios can both be understood as phenomena for which it is impossible to construct a faithful classical causal model. This gives us a unified way of understanding these two conceptually different quantum phenomena as violations of the classical framework of causality. And so this also generalizes earlier results, confirming that this relation between fine-tuning and Bell-Cauchy-Specker inequality violations is fully general. Thank you.